So last time we've talked about the solutions to series puzzle, and we arrived at some very interesting solutions. So what we had is we had a situation, we had several different circuits, but all of the circuits shared the same feature. You had one resistor, and then you had branches, and some of those branches had only one LED, like our initial solution, which had 6 LEDs. So we had this solution, then another solution was something that looked like this, where we had 2 branches, and each branch had 3 LEDs in them. And we had a solution in the middle where you had 3 branches and 2 LEDs, so you guys get the idea. So all of these solutions have shared one feature between each other. They all had just one resistor. And that feature was really forced on by me because I told you that series puzzle must have just one resistor. But if we actually take off that particular restriction, then we can do a very different circuit. Okay? And that circuit, there are a lot of really good things going for it. And in many ways, it is superior to the circuits that you're looking at right now. But when I say many ways, I don't mean always, okay? Remember when you guys did your paragraph on which solution to series puzzle you liked best? There was really no right answer. It depends on what you're optimizing for. So let's go ahead and take a look at another solution that uses more than one resistor. And this is very, very straightforward because all you do is you put a resistor inside the branch. So what right now I'm doing, I'm modifying this circuit, and instead of having this resistor outside of the branches, I'm going to pull it inside. And I'm going to have one resistor in every single branch. Now, I don't want to do 6 because we don't really need to. They're all the same. So I'm just going to do 3. And this situation allows us to have a lot of control over a circuit. Because over here, we were basically forced to have the same current in all of the branches because the resistor is what controls the current. So in this situation, we can have different currents in different branches. And you should be asking, well, why would I want that? Like, what's the point? Well, this is where the reality and the simulation doesn't match. So let me explain to you and show you exactly what I'm. So I'm going to go ahead and build the circuit. So I'm going to grab my breadboard, and I'm going to go ahead, and we had 6-volt batteries last time. I want 4.5-volt batteries this time. So I'm going to go ahead and connect my battery. So I've got negative here, positive here. I'm going to go ahead and straight away route my power to the top and route my ground to the top as well. So now I have ground all the way and power in all of the rails over here. So now this is just straightforward stretching this out, right? So the power, here's my first branch, here's my LED. I'm gonna take it straight down to the bottom. Here's my second branch, here's my LED. Once again, they're connected in the same column, take it straight down to the bottom. And here's my third branch and LED, and take it straight down to the bottom. So the situation that we've had over here in the circuit is that all of the voltage drops were exactly the same because all of the LEDs were exactly the same. In real world, this doesn't happen. Even the same color LEDs differ from each other a little bit. Some of them can have slightly larger voltage drops than others. It's just true. So if you want them to light up with equal brightness, you have to have resistors in each branch so that some of the resistors will take a little less and some of them will take a little more. But that's not all. If I were to change these colors and let's say make this one blue and make this one green. If I were to build this type of circuit with different color LEDs inside it, most of these LEDs will not light up in real world. They will unfortunately light up in Tinkercad because it doesn't give you LEDs with different voltage drops. But in real world, they absolutely will not light up. And the reason for that is because in real world, different color LEDs have different voltage drops. So for example, and this is an example, but this is an example informed by a lot of experience, okay? Blue LEDs tend to have voltage drops of about 3 volts. Green LEDs tend to have voltage drops of about 2.2. And red LEDs usually come anywhere between 1.5 to 2 volts. So we can keep this one as 1.8. So you see what I'm saying? If we were to have this situation in this circuit, so let's say you have a red over here, a green over here, and a blue over here. These LEDs have different KVLs. Think about it, right? The loop with red LED has a resistor and a red LED in it. So once red LED takes in 1.8, the resistor takes the leftovers. But the other loop, the one with the blue LED will take 3 volts, not 1.8. So the resistor simultaneously would have to have 6 different voltage drops. Of course, the resistors don't do that, right? Instead, they choose the biggest voltage drop they can have, and then only your red LEDs light up. So this sort of setup is a setup that allows us to deal with this issue. So when you have this type of circuit, each LED can have its own voltage drop, and it will still light up. So let's go ahead and figure out how this works. So the very first thing I need to do is, here's my red loop, and I'm making it red not because it's power, but because my LED is red. And for red loop, my KVL is going to be voltage of the battery equals voltage of the resistor, let's call this R1, because we have 3 of them, plus voltage of red. All right, so if the battery is 4.5 and the voltage drop of red is 1.8, what is the voltage drop of our R1? Okay, so what's going on here? Well, obviously, you just need to solve for V of R1, right? So V of R1 is going to be voltage of the battery minus V red. And that is, of course, 2.7. All right, so now that we have the voltage drop, all we have to do is specify the current and we can find the resistance. And this is really where the meat of this comes, right? Because we can control the current in every single branch. So when you light up your LED, its brightness depends on 2 factors. If it's getting enough voltage, and also how much current you're pushing through it. So for example, reds can be very, very dim. It's the lowest visible light. And red LEDs tend to be quite dim, right? So maybe we want to put a little bit more current through it so that my red LED becomes a little brighter. So what if I say, okay, well, I want the current in this branch to be 10 milliamps. That's a lot. That's a lot of current, right? But I want it as bright as possible. So 10 should be enough. So this is it. So I've set up my current. All I have to do now is figure out what is my R1. And this is just your Ohm's law, the voltage drop of R1 over I1. And I've decided that one's going to be 10. So this is 2.7 divided by 0.01 amp. It is, of course, 270 ohms. Okay, so this one was 270 ohms, but here's the crazy thing, right? We can do a different branch. Like when we do the green branch, we can set a different current easily enough. So let's go ahead and do that. So next I'm going to go ahead and do my green branch. And this is my R2. So the KVL for green branch is going to be voltage of the battery equals V of R2 plus voltage of the green. So what is the voltage drop of R2? We know that voltage of the green is 2.2. So what would be the voltage drop of R2? So 2.3 volts, right? Very, very, very straightforward. So I can use exactly the same method and find my R, right, as long as I set up my current. Well, I don't need my current to be as much as it was through my red in this case, and I'll tell you why. Because green LEDs are just brighter than reds. If you ever hook them up and look at them, this is the things that unfortunately you need real experience in the classroom to see. So we don't need as much current over here, so we can just easily get away with, say, 5 milliamps. All right, so if the current is 5 milliamps, what is going to be the resistance? So go ahead and calculate that and tell me what that is. And the formula is, of course, Ohm's law. The voltage drop of R2, which we have found, over the current that goes through I2, goes through the branch, and that's I2. So go ahead and find what that is. So what's going on over here? So we've got R2. This is the voltage drop of R2 over I2. So the numbers are 2.3 volts divided by 0.005. When you put this in, it's 460. So here's the crazy thing, right? We can add another LED into that branch, and there will be no consequences. Remember how in this case, all the branches had to look the same because they had to have the same voltage drop. But since we no longer have that restriction, we can add another LED in there if we can, right? And since our voltage drop of the resistor is 2.3 and the voltage drop of green is 2.2, I can easily stick another green in there. Or if I like, I can stick another red in there. So I'm going to go ahead and do that right now. So what I'm going to do is I'm going to erase this wire over here, and I'm going to add another LED, and I'm going to make it red. And I'll tell you why, because we haven't been able to do something like that, to have different color LEDs and different number of LEDs in each branch. But we can now. So now I have two LEDs, green and red. Well, that would mean I would have to redo my calculation, of course. But the calculation, the basics of the calculation are still exactly the same. So the very first thing that we're going to do, our KVL is going to change, right, for my green branch. My KVL is going to change, and now I'm going to have the voltage of the green plus voltage of another red. Well, what are these two together? If these two are 4, then what is our new voltage drop of R2? And it is, of course, 0.5, right? You just subtract one from the other. So 0.5 volts. Okay, so now, once again, we're keeping 5 milliamps from our last time. So we have 0.5 volts divided by 5 milliamps. And we can easily find our resistor. So voltage drop of R2 divided by I2. So why don't you guys tell me what that is? So what you have is you've got 0.5 divided by 0.005. This is, of course, a 100 if you put this into a calculator. Very, very, very straightforward. So the nice thing about this circuit, right, you can have as many LEDs in the branch as your battery would allow. And right next to it, you can have a branch with just one LED. All right, so this is everything that I wanted to show you today.